Welcome back to the second half of section 3.2 on logarithmic functions and their graphs. So in the first half of this section, we looked at logs of base 10. Now we are going to look at what we call the natural log, or log base e. Like I said, since e is its own special fancy number, very similar to pi, we have its own function associated with it, the natural log. And oftentimes we will be using the natural log of things, and it has many great real-world applications, though we're not going to do any real-world problems with this. The textbook, if you do have one at home, does give an application inside psychology. Like I said, there are many other applications of these logs and exponential functions that would be discussed in section 5, which we're not fully hitting. But at the end of the chapter in a recap video, I will make sure to talk about some of those applications. So let's get started with some basic properties. So log base e of x is the same as the natural log of x. So instead of writing log base e, log base e, log base e the entire time, we are just going to write the natural log. Natural log is always abbreviated ln. So, here with this first property, again, we saw this yesterday, the natural log of 1 is equal to 0 because, like we said yesterday, anything to the 0 power is 1. So, e to the 0 power also has to equal 1. Property number 2, the natural log of e is just 1. So natural log undoes base e. So natural log of e is just 1. Natural log of e to the x is just x. Because again, that natural log is undoing base of e. We'll talk about that more in solving and why I keep using the word undoing. And we'll see it undoing it in there. This is our inverse property. The natural log undoes base e. And then our fourth property is if the ln of x is equal to the ln of y, then our x and y values have to be equal to each other. So, in our next example, this is going to be very similar to what we did in the first section. So that's why I broke it into 2. Hey, we're getting our bearings with logarithms. Okay, you had hopefully your questions answered. You practiced with it. Now let's see what happens when we use a natural log. So it will be more practice of the same. So example 5 from our notes in this section, we'll just say, what is the natural log of 10? Now, natural logs are going to be incredibly difficult to calculate in your head unless it's something like this. If I see natural log of e to the 5th power, I know it's 5. Do I know what e to the 5th power is off the top of my head? No. Am I going to calculate that easy off the top of my head? No. But that's why we have our calculators. So the nice part is, since natural log is such an incredibly common function, if I have my Desmos calculator here, again, I want to go functions. Under miscellaneous, we will see ln listed here. So all I have to do is ln of 10. And there we go. It gives me the answer. 2.3 0.02, and that would get rounded up to 6. So again, I'm asking for 4 decimal places. I do see the 8 after the 5, so please make sure to round it up. I won't be overly concerned if there are minor rounding errors, but you guys are seniors. We should be rounding right, okay? So our answer is, for this, again, this is all just in the calculator, 2.302, or sorry, 6, because it rounds up. Now, let's think about what E is as a number. E is like 2.7 something. So, 2 cubed is 8. 3 squared is 9. You know, that if I do, you know, it's closer to 3 than 2. So the log base 3 of 10 should be a little bit over 2. Natural log of 10, again, should be a little bit over 2. But again, just utilize your calculator with natural logs. I wouldn't go too crazy on trying to figure them out in your head. So the next thing we're going to do is we are going to talk about the domain and range, and we are going to sketch a graph. Now, in the notes, it necessarily didn't say sketch a graph, but I will add the graph on here because that will help us make more sense of our domain and range. So moving on to example 6, we are looking at the function f of x is equal to the natural log of x plus 3. Now remember, this means shift left 3. Remember, when it's inside the function like this, it moves in opposite. We're used to positive go to the right. This actually shifts it to the left. We've been doing this shifting of functions in chapters 1 and 2, so hopefully this is still feeling very familiar. So if I'm shifting left 3, my vertical asymptote and my y-intercept will both get shifted left 3. So my original vertical asymptote was the y-axis. If I shift that left 3, that is now a vertical asymptote at x equals -3, which will imply for my domain that x is greater than -3. So remember, it's going to come up this way. Now, my original x-intercept was 1, 0. If I shift that left 3, that's 0, 0, -1, 0, -2, 0. So that gets shifted over here. X-intercept is -2, 0. Again, go right along the asymptote. Then it will grow something like so. It might actually taper off a little lower. Again, this is just a rough sketch. Now my range, again, is all real numbers. So, we have a domain getting shifted over. Our default domain is x is greater than 0 for these logarithmic functions, whether it's a log base 10 or a natural log. That does not change. Our domain does not change. So since I shifted it left 3, I shifted my asymptote left 3. So again, left 3, shifted my y or my x-intercept of 1, 0, left 3. Now my range, this will always go up and be all real numbers. So let's again take a look at this graph and use this to verify what we're looking at. So we will see this graph here in green. All I did was type it in. If we look close, I know Desmos never draws in the asymptotes, but it does appear to have an asymptote here at -3, like we drew here. And we do see a y or an x-intercept there. As you see, mine went a little high as my y-intercept is up there. If you want to pull a y-intercept from Desmos, just like I did by clicking on it, that's not a bad thing, and it could have helped some more with the accuracy of the graph. But again, this is a rough sketch, and that is okay. So, the final thing we are going to look at is an application on finance. So in section 1, we talked about continuous interest and how that works. So we are going to utilize an equation that helps us find out some information about what happens when we compound continuously. So this is example 7 from your notes. This is just an example of a real-world application. Again, for homework, you do not need to apply any real-world applications. So example 7 says, a principal P invested at 6% interest and compounded continuously increases an amount of K times the original principal after T years, where T is equal to the ln of K divided by the interest rate of 6%. So first thing it asks us to do is how long will it take to double? So doubling investment, and then we'll look at tripling. So doubling would mean my K value is equal to 2. If I want to know when the investment is 20 times greater, I put K at 20. If I want to know when it's 2.5 times bigger, again, just put in 2.5 for K. So let's utilize this function here. Time is equal to the ln of 2 over 6%, or 0.6. Or sorry, 0.06. So again, this is just going to be a matter of typing in the calculator. Finding the natural log of 2, not an easy task. So this is all calculator here. Please make sure you just type in correctly and accurately. So function ln of 2. So I want to close those parentheses to make sure the division bar goes outside the natural log of 0.06. So here with this, I know I've been saying go 4 decimal places. I'm looking at this as a real world problem. Going 4 decimal places when I'm talking about years is not fully necessary. I'm just going to round it off after 2. So it's going to take a little over 11 and a half years to double your investment if we are getting 6% interest compounded continuously. Not too bad. If, hey, I just sat on my money for 11 years and I had twice as much, I wouldn't be complaining about that. So, again, just typing that in, that gives me 11.55 years. Now, the next thing it asks is how long will it take to triple? So the next question said triple. And in order to do that, we are just going to say k equals 3. So all I have to do is adjust what's inside the ln from 2 to 3. And that's the nice part about me doing this, is I can just literally edit the equation we just typed in. Not going to have to retype the whole thing. I'm just going to hit delete, change the 2 to a 3, and find out that it takes 18.31 years. So it takes a little bit, let's see, 18.3, so let's see, quarter of a year, almost 18 years and 4 months to get to tripling your money. Again, not a bad return there. So, that is equal to 18.31 years. So, here with this, again, how this can be nice to look at is looking to the future in your finances. If you look at retirement accounts, you know, sometimes sitting on money, it may seem like 18 years is a long time, but if it's a retirement investment, you know, okay, it took 11 and a half years to double. Only took 18 years to triple. So, you know, the amount of money doubling, okay, if I had $100 out, that's $200. I get another $100 out of it. It took 11 years to make the first $100. To make another $100 off of it, it only took 7 years. So, you know, this shows this growth can be really good for you if you just sit and wait on your money. So, that's going to wrap up these notes. So our final classwork, or homework, is on page 200. You are going to complete 77 through 88 all, then 94 through 98 even. Hopefully this gives you some good practice on the idea of what logarithms are. We will be exploring logarithms again in section 3 and section 4 and diving deeper into what they are. Thank you for watching.